I want you to picture the ultimate chicken and egg problem.
Okay, I'm with you. Like a causality loop.
Yeah, exactly. But instead of a farm well, imagine we are standing inside this massive, humming data center.
Right.
Because we know that to get an artificial intelligence to actually follow instructions, to, be a helpful assistant rather than just a rambler, you need data.
Massive amounts of data, and specificated too.
Right. You need instruction tuning data. You need thousands upon thousands of examples where a human says, do X, and the machine sees the correct output for X. But here is the catch. Humans are slow.
Very slow.
And we are expensive. And frankly, when it comes to writing 50,000 variations of how to summarize a meeting, we get bored.
Yeah, we aren't exactly scalable, and that is the bottleneck. High-quality human data is basically the gold dust of the AI industry. It is incredibly scarce and, like you said, incredibly costly to produce.
So the bottleneck for building better AI is us.
Unfortunately, yes.
But what if it didn't have to be? What if you could take a raw, untuned language model and just tell it, hey, figure out your own training data?
Now that is the holy grail. Bootstrapping intelligence.
And that is exactly what we are unpacking in today's deep dive. We are looking at the paper Self-Instructing.
Aligning language models with self-generated instructions.
Exactly. It is from the ACL 2023 conference coming out of the University of Washington and the Allen Institute for AI.
This paper really is something of a modern classic because it challenges that fundamental assumption we just talked about, that you need an army of humans to train an AI.
Right.
They're proposing a pipeline where the model generates its own training data, essentially pulling itself up by its own bootstraps.
Which on the surface sounds like a snake eating its own tail, or like trying to learn fluent French by only talking to yourself in broken French.
It does sound completely circular, but as we will see, it is less about learning new facts and more about unlocking latent abilities that are already sitting there, just hidden in the weights of the model.
So before we get into the how, the pipeline itself, let's set the stage regarding the technology for you listening. We are talking about vanilla language models here.
Right.
So think GPT-3 before it became ChatGPT.
Exactly. A vanilla model is essentially a very, very sophisticated autocomplete.
It just predicts.
Yeah, it has been trained on the entire internet. Wikipedia, Reddit, Common Crawl. So it has seen everything. It knows facts, it knows grammar, it knows code. But its objective function is simple: predict the next word.
So it is a probabilistic engine. If I prompt it with write an email to my boss asking for a raise, a vanilla model might not actually write the email.
No, it wouldn't.
It might just complete the sentence with, is a terrifying prospect for many employees.
Precisely. Because it continues the text, it doesn't follow the instruction. To fix that, we usually do instruction tuning.
Where we show it the thousands of pairs. Here's an instruction, here is the output.
Right. But historically, getting those pairs meant relying on huge data sets like prompt source or SuperNight.
And those are the human-curated ones.
Yeah. And the paper highlights a few major issues with those human data sets beyond just the literal financial cost.
Right.
They argue that humans aren't actually that creative when we are put on the spot.
We are creatures of habit.
We really are. If you ask a room full of people to write tasks for an AI, 90% of them will say, summarize this news article.
Or translate the sentence.
Exactly. The diversity of tasks in human data sets is actually surprisingly low. We gravitate toward what we think an AI should do rather than exploring everything it could do.
So the hypothesis of the Self-Instruct paper is essentially the vanilla model has read the internet.
Yes.
It has seen billions of examples of instructions and responses out in the wild, in forums, in tutorials, Q&A sites. The knowledge is in there. It just doesn't know how to format or prioritize it.
That is the core insight.
Yeah.
They believed the capabilities were latent. They just needed a mechanism, a pipeline, to elicit them, capture them, and then feed them back into the model to reinforce that specific behavior.
Okay, so let's walk through this pipeline. Because I was looking at the diagram in the paper, and it is a 4-step loop. But it doesn't start from absolute zero, right? There is a spark to get the engine running.
Right, they call it the seed.
And I have to say, I was completely shocked by how small this seed was. 175 tasks.
That is it.
In a world of billions of parameters and terabytes of training data, 175 tasks is just a drop in the ocean.
It is statistically insignificant in terms of volume.
And these are manually written.
Yes, human written, just really simple things like brainstorm a list of New Year's resolutions, or classify this movie review as positive or negative.
So why 175? Why not just start at 0?
Well, you need to show the model the format. You need to establish the pattern of instruction followed by instance. It is like showing someone a template.
Ah, yeah.
You aren't teaching them the actual content. You're just showing them the layout of the form they need to fill out.
Okay, so they have this tiny seed set. Step 2 in the pipeline is instruction generation. This is where they ask the model to get creative.
Yeah, they take a random sample of those seed tasks, say 6 or 8 of them, and they feed them to the vanilla model as a prompt. And the prompt basically says, here are some tasks. Now come up with a new task.
It is like an improv game. Here is a scene, now you invent the next one.
Exactly. And they have to be careful here. They don't want the model to just rephrase the seed tasks.
Right, if the seed is write a recipe for cake, they don't want write a recipe for pie.
No, they want broad coverage.
Yeah.
They want the model to explore the entire task space.
So they want things like debug this Python code, or write a sonnet about a toaster, or plan a heist in a fictional city.
Right. And surprisingly, the model is very good at this. Because it has read the internet, it knows all the random things people ask for.
Yeah.
It starts hallucinating, in a good way, all sorts of different jobs it could do.
Okay, so now we have a new instruction. Let's say the model generated. Verify if this statement is a scientific fact. Step 3 in the pipeline is classification. Why do they need to classify the instruction?
This is a really subtle but completely crucial engineering detail. The system needs to analyze the instruction it just created and decide, is this a classification task?
Meaning, is the answer a defined label, like yes or no, true or false, category A or B?
Exactly. Versus a generation task, like write a story, where the output is open-ended text.
But why does that distinction matter enough to be its own dedicated step?
Because it dictates how they generate the answer in step 4. And this leads us to what I think is the most technically interesting part of the whole paper, the distinction between input first and output first generation.
I read this section 3 times to make sure I got it. This is where they prevent the model from cheating, essentially.
That is a really good way to put it. Let's look at the input first approach. This is what they use for normal creative generation tasks. Say the instruction is, write a travel itinerary. The model generates an input first, maybe a 3-day trip to Tokyo, and then it generates the output, which is the itinerary itself.
That makes perfect sense. The model flows naturally from the instruction to the input to the output.
Right, but for classification tasks. Let's say the instruction is, identify grammar errors in this sentence. If you use that same input-first approach, what do you think happens?
Well, think about the model's bias. It is trained on published books and articles. It is trained to predict the most likely, coherent next sequence of words. So if you ask it to generate an input sentence,
Yes.
it is going to generate a good sentence.
Exactly. It generates a grammatically correct sentence because that is what it knows how to do. So you get the cat sat on the mat,
Yeah.
and then the label it generates for that is no error.
And if it does that 10,000 times, you end up with a training data set where every single answer is no error.
You completely collapse the task. The model learns that the answer to check grammar is always correct. It literally never sees a negative example.
So you end up training a model that thinks errors don't exist. It learns to be a total yes man.
Exactly. So for classification tasks, the researchers flip the script. They use an output-first approach.
Meaning they pick the answer before the question.
Yes. They tell the model the instruction is identify grammar errors. First pick a label. Let's say error present. Now generate a sentence that matches that label.
So they force it to break its own rules. They force it to generate the bad grammar because the label demands it.
It creates the hard negatives. It creates those rare cases.
Yeah.
This balances the data set, so the model actually learns the difference between right and wrong, rather than just assuming everything is always right.
That is such a clever workaround for the model's inherent bias toward being good. It is like telling a student, hey, I want you to write a wrong answer on purpose so we can analyze it.
It really is. Without this step, the data set would be huge, but totally shallow. With it, you actually get depth.
So we have this loop running. The model invents a task, decides what kind of task it is, and then generates the input and output using this clever flipping technique. But we're talking about a vanilla model here. It is not perfect. Surely it generates a lot of absolute garbage.
Oh, absolutely. If you just let it run unchecked, you would get a massive amount of noise.
Yeah.
Section 3 of the paper is all about their filtering process. They generated something like 52,000 instructions, but they had to have a rigorous bouncer at the door.
So what gets kicked out?
First, duplicates. They use a metric called RUEE.
Which is basically a similarity score, right?
Correct. It measures text overlap. If a new instruction is too similar to one that is already in the pile, it gets tossed. They're optimizing for diversity, not volume. They don't want 500 ways to say, how are you?
Right. They want the model to stretch its legs.
Exactly.
Yeah.
Then they have heuristics, basically simple rules. For example, if the instruction asks for an image or a graph or sounds like a software UI command.
Like, click here to download.
Right. The model is text only, so those tasks are literally impossible. They filter those out. They also check if the input and output are identical.
Which would be a pretty useless task to train on. Say hello, hello.
You would be surprised how often models get into lazy loops like that. So after all this filtering, they ended up with about 52,000 usable instructions and 82,000 instances.
And when they looked at what remained, what did they actually find? Was it just more of the same boring summarize this type tasks?
No, and this is the really cool part. They did a verb-noun analysis to visualize the diversity. In the seed tasks, those initial 175 human ones, the verbs were pretty standard, write, translate, list.
Sure.
But in the synthetic data, they saw things like design, verify, simulate, climb.
Climb.
I am not sure what digital mountain it was climbing, but it shows the model was exploring concepts well outside the standard NLP benchmarks. It was inventing tasks related to software design, role-playing, scientific verification.
And importantly, when they compared this new synthetic pile to the original seed pile, there was very little overlap.
Less than 5% overlap.
Which proves the core hypothesis. The model wasn't just memorizing the examples, it used them as a springboard to jump into completely new territory.
That is the bootstrapping in action right there. Okay, so they have built this massive machine-made curriculum. Now comes the moment of truth. Does studying your own notes actually make you smarter? They took this data, fine-tuned the vanilla GPT-3 on it, and called it GPT-3 SELF-INSTRUCT. How did it do?
The results were, frankly, startling. They tested it on a benchmark called SuperNI, which is a big collection of standard NLP tasks. Logic, reading comprehension, that sort of thing.
And how did the vanilla model do before the training?
Terrible. Near zero. Because, again, it didn't know it was supposed to be solving a task, it was just predicting words.
And the self-instruct model?
It improved performance by 33.1%.
Wow, that is a massive jump. That is the difference between a completely broken tool and a working one. It is huge. But the comparison is what really matters. It outperformed the T0 model, which was trained on massive data sets that involved thousands of hours of human labor. And it came within striking distance of Instruct GPT-001.
And just to clarify for you listening, Instruct GPT-001 isn't just some random baseline model. That is the open AI model trained with private user data. Real queries from real people.
Correct. So you have a model trained on expensive, private, real-world human data, and a model trained on data it hallucinated in a locked room, and they were performing almost at the exact same level.
That really challenges the whole data is the new oil narrative. If you can just synthesize the oil, the scarcity disappears.
It certainly shifts the value. It implies that the secret sauce isn't necessarily holding the data, but having the pipeline to generate it. But the researchers knew that academic benchmarks like SuperNI are a bit dry.
Yeah.
They don't always reflect how you or I actually use AI. We don't ask it to perform sentiment analysis on this string. We ask it to write an email to my landlord about the leak.
Right, so they created their own test set.
They did. A set of 252 user-oriented tasks. Email writing, brainstorming, coding, productivity stuff. And because these are completely open-ended, you can't just check a box to grade them. They had to hire human raters to grade the responses A, B, C, or D.
And
The self-instruct model blew the other public models out of the water. And against Instruct GPT-001, which was the industry standard at the time, it was only behind by about 5%.
a 5% gap. That is dangerously close for a method that requires zero humans in the loop.
It suggests that for the vast majority of things we ask AI to do, the model actually already knows how. It just needs to be unlocked. The barrier isn't intelligence, it's alignment.
However, I have to play devil's advocate here.
Please do.
We are letting a machine teach itself, and we know these models have absolutely no concept of truth or physical reality. There had to be some glorious failures in that data.
Oh, there definitely were. The paper is very honest about the limitations. They call it the long tail problem. The method works great for common concepts, but if you ask it to do something rare or complex, the synthetic data really falls apart.
And because the model has no common sense, it can generate instructions that are, well, let's say ill-advised.
Yes. There was one example in the bad generations table that really stuck with me. It completely highlights the danger of blind trust. The instruction generated was, the house is on fire, go.
High stakes.
Very.
Yeah.
And the model's generated solution. It said, go to the kitchen and take a pan. Take water from the tap. Pour water into the pan. Put out the fire with the pan.
Wow. I mean, functionally, yes, water puts out fire, but procedurally, if my house is burning down, I am definitely not looking for a saucepan.
Exactly. It mimics the structure of a helpful step-by-step guide perfectly.
Yeah.
But the content is grounded in zero reality. It is a perfect example of hallucination in the training data itself.
It is the blind leading the blind.
And there were coding errors, too. It would write a perfectly formatted description for a Python function, and then the actual code it generated would do something completely different.
So if you train a model on that, you are teaching it to lie, essentially. You are baking in errors.
Yes.
So how do we actually solve that? Because if the teacher, the model, is slightly confused, the student, which is also the model, is going to be even more confused.
Well, the paper hints at a really elegant solution, the distillation effect.
Okay.
They found that if they used the pipeline to generate the questions, the instructions, but then used a smarter model to answer them.
Wait, so use the vanilla model to brainstorm the curriculum, to come up with the questions, but bring in a professor model to write the textbook?
Exactly. They used Instruct GPT-003, which is a much more advanced model, to generate the output for the synthetic instructions. When they did that, the performance jumped another 10%.
That makes a lot of sense. The vanilla model is creative enough to ask good questions, but maybe not smart enough to answer them perfectly.
Correct. This tells us that self-instruct is a valid framework, but the quality of the teacher inside the loop is the limiting factor. It also points toward a huge future trend of model distillation. Yeah, it is the idea of compressing intelligence. You can have a massive, incredibly expensive model running in a data center generating high-quality training data. And you use that exact data to train a tiny model that lives locally on your phone.
Oh.
The tiny model learns from the giant one.
So the giant model does all the heavy lifting, and the small model basically memorizes the answers.
In a way, yes.
Yeah.
It democratizes the capability. You don't need $1 billion to build a useful AI anymore. You just need a smart pipeline and a few hundred seed tasks.
It turns a resource problem, we need 1 million humans, into a compute problem. We just need to run this loop for 24 hours.
Exactly. And that is an absolute game changer for smaller labs or companies that can't afford to hire a massive annotation team.
But I want to end on a slightly more philosophical note for you all listening. We are entering an era where a significant portion of the internet, and therefore future training data, will be generated by AI.
The ultimate feedback loop.
Right. And we've talked about AI learning to do human tasks better by training itself. But if this self-instruct loop runs indefinitely, eventually, might it optimize for tasks that make perfect sense to a neural network, but are entirely incomprehensible to the human mind?
That is a wild thought.
Are we bootstrapping a helpful assistant? Or are we seeding an alien intelligence that will eventually outgrow human logic altogether? Like, what if the tasks it invents 50 loops from now are things our brains literally can't process?
That is the big unknown. Synthetic data solves the quantity problem today, but it puts even more pressure on what we are actually optimizing for tomorrow.
We're moving from being the writers to being the editors.
That is a great way to put it. The human role shifts entirely to curation and boundaries.
Well, this has been a fascinating look under the hood of how these systems are evolving to, well, evolve themselves. The paper is Self-Instruct, and it is definitely one to bookmark if you are following the trajectory of language models.
Absolutely. It is a really pivotal moment in the timeline.
Thanks for diving in with us. We will see you on the next one.